Hi, I'm Owen, captain of 1843 at Wolfpack Machina.
And I'm Chris, also captain of Wolfpack Machina.
As part of our collaboration with the Boston Tech Initiative, we are going to do a walkthrough of our 2020 Ultimate Goal robot.
We hope that this video will be helpful for new teams who are starting this fall and to learn about how a robot is constructed and the important design considerations you need to take.
Additionally, we hope that this walkthrough will also be interesting for more experienced teams.
All right, let's get started. So first we're going to talk about the different materials we use in actually constructing our robot. Now, the majority of our robot is made out of aluminum. We actually have a CNC machine in-house which allows us to mill and shape our own parts, which is super helpful, and that's how we get all these custom designs with all the holes in the exact places that we need them to actually construct the robot. Now, aluminum is very good because it is a light metal, but it is still very strong, which means we can use it all over our robot as this plate, which is the main structural plate of the robot, and it supports a lot of the parts of the robot, such as the shooter and the intake. But at the same time, it doesn't add too much weight to the robot to the point where it messes with the actual driving capabilities or the speed of the robot as we move. So yeah, so the majority of our robot is built out of aluminum for some things, like stylistically, for some things for strength, and it's a super great material to work with. And the material we use the second most is definitely polycarb. Polycarb is another material that we are able to work with and design and cut pieces ourselves on our CNC machine. And we use polycarb all over the robot in different places for different scenarios. Now, polycarb itself is a very malleable material. It's really easy to work with. We can bend it into different shapes and put in different holes all over the place. So it's used for things like here, funneling, like getting rings into the magazine or the shooter or the up ramp, where the structural and like the strength of material isn't quite as important as the functionality. It's also see-through if there's ever places like the magazine where it's helpful to be able to see in and see if you have rings or something like that. So yeah, polycarb's a great material to work with. Then when there's a part of the robot that has a lot of stress on it, we will use stronger metals such as steel. For instance, in here on the shooter, we have these two really high-powered motors that spin super fast to power the shooter. So it's really important to get steel gears in there because aluminum would have just been too soft and the gears would have just kind of like been crushed down and need to be replaced frequently. And so the best option was steel. Another thing that we use is rubber or tubing. And so this is for a lot of places where we need a little more flexibility, where, for instance, on our intake, rings coming in can come in at a bunch of different angles, and so it's helpful to have something that can move, but also like still strong enough to move rings up the intake. So we use rubber all over our intake for our tubing, all over the rollers, in other smaller places where we need extra stability or a little extra durability. And then lastly, something we learned a little bit later into our season is the importance of Loctite. Our robot has a super high-powered shooter on it that when the way we run our strategy is constantly spinning, which means the robot's vibrating, and in in-person matches you're bumping into other robots and you're moving all the time, which means everything in the robot is constantly shaking and vibrating. And what you may not realize happens because of this is that screws can come loose and they just fall out in the robot. And sometimes that's just like out here on the standoff that doesn't matter, but sometimes it's in really important places on the inside of the robot that are really hard to get to. So what Loctite does is if you put it on your screw before you screw it in, it kind of acts like a glue or just the way that it sets, and it makes the screw really, really difficult to ever come out again. And it's super helpful for screws in places that deal with a lot of vibration to keep the screws in for a super long time. So overall, in our materials, there's a few things we look for. We look for like structural stability, the strength of materials, where they might be helpful to use, and like places where you can use polycarb realistically. Also, we like to be able to use our materials more creatively, which is why it's super helpful for us to be able to shape our own aluminum, to have the pocketing, to even use on like sprockets and that sort of thing. And then also the cost of things. Some things are more expensive than others, obviously, so we have to use aluminum a lot of the time, but for any places where we can use polycarb or a cheaper material, we try to go to there. So yeah, I think main things we look for is when we're looking at a subsystem or a part of the robot and what material we might use there, we think about the structural needs of that part, the stress that it'll be under, and again, price efficiency for that part of the robot.
Wolfpack, another three into that top goal, 272 to 262 with less than 50 seconds remaining in this match. This is going to be a close one.
All right, so the first mechanism on our robot that we're going to talk about is our drivetrain. So I think this is the best mechanism to start out with because a drivetrain is usually the most effective thing to build early on in the season because it's not game specific for the most part. You could have even our weird game that we made for our summer camps here, and you would still be able to make a drivetrain that would most likely be mostly applicable for another year. And it also allows you to just have a good test bed early on in the season for anything you want to test out. So if you come up with like an intake design or a depositor design, a scorer design, you can just throw it on your drivetrain. You can test it out from the beginning. And you can really just carry on that sort of thought process into actually building your drivetrain because it's a really great place to start out structurally on the robot. So our drivetrain in particular is a Machina wheel drivetrain, and I'm not going to go too far into how those work because there's plenty of resources online for that, but essentially 4 Machina wheels, and you're going to have 2 of each side. There's 2 different types of wheels, and from the top, all the rollers should form an X pointing towards the middle. And going further off of that, we chose a parallel plate design, which is a really great design for if you have access to custom parts or have access to order custom parts because it supports the wheel axle on both sides of the wheel, which prevents any sort of chance that the axle might bend and the wheel might droop over time. So it just gives you a very, very solid support for your wheel. And another benefit of this design is that it allows you to have these big inner plates or outer plates or however you decide to ultimately support your robot. In our case, we chose inner plates, and you can see this whole entire inner plate supports the wheels, the intake motors and gears right here, all of the intake rollers, and the shooter, which just allows the robot to be very cohesive and structurally sound. And the next thing about a drivetrain is to have a very, very solid power transmission because this is going to be driving your robot around for the entire season. You're going to want it to be very, very secure. So usually what you really don't want to do is mount the wheel directly to the motor axle because then if anything happens to the wheel or the motor, you might end up bending the axle, which is no good. You don't want to bend your motor axle. That is very expensive. So in our case, we chose a chain and sprocket system, which we just chose because the steel chain is very, very, very strong, and we just wanted to be extremely sure in our design. And another thing you have to think about when powering your wheels is to get a good gear ratio. So we chose a 435 RPM motors from GoBuilda, or a 13.7, I believe, to 1 ratio, and then have a 16-tooth sprocket here and a 20-tooth sprocket here on the wheel, leading for an effective 17.1 or 17-to-1 ratio on the final wheel, which we chose just for a good balance between strength and speed. And in hindsight, we honestly could have made this faster, closer to 15-to-1 or 16-to-1 or anything like that. So that's just a good starting place to start out with your drivetrain. Somewhere in that range is definitely good. And another very important thing to think about, especially for Machina wheels, is to guard your wheels from any sort of contact with other robots, especially Machina wheels, because they have all of these intricate rollers and axles, and if they're hit really hard by another robot, there's a chance that they might fall out, and then your robot's not going to be able to drive well anymore. So parallel plates are very good for this because you have an aluminum outside shield against contact, and also these standoffs in the front help with that as well.
So next we're going to talk about the core of our robot, which has 2 main purposes. It houses the majority of all the electronics in the robot, as in a lot of the motors, 4 of the motors, and also both of the hubs. But what's really important initially about designing a robot core is it is super significant and integral to the actual structural stability of the entire robot as a whole. So as we were talking about how that's super important to keep your drivetrain supported and how we use this big plate in the middle, what actually holds the 2 separate channels of the drivetrain together is the robot core. So if you can see here, we have 1 beam running down attached by quad block mounts and a U channel on either side, which keeps these plates together kind of towards the front of the robot, and then also one at the very back of the robot with the same design with the quad block mount on either end of what can usually be a U-channel. What this does is U-channel and pod block mounts provide really good support and a lot of strength. It means that your robot can't come apart, it's not shaky, it's super strong, and that's really important when you're trying to, drive and you're into in-person play and robots are bumping against each other. You need your whole robot to stay together. So the structural stability of the robot often comes down a lot to the core of the robot, which we talk about as this area right here. Now, the other key parts of our robot core after structural stability is taken into account is how we house the electronics. The two things that are really important for the hubs is you want them to be accessible, very accessible, because you're going to be doing different wire switches. Maybe you break a servo and you need to replace it, or maybe you're trying to figure out if a different port doesn't work. So the ports of your actual hubs need to be accessible, which is why we have these cutouts in the polycarb on the bottom. It makes it really easy to get into the different ports and adjust our wiring without having to take anything off or disassemble any parts of the robot. And so we mounted both of the hubs downward facing with this polycarb plate on the bottom, which helps to keep all the wires inside of the robot. Because wire management, super important. We don't pretend to be the best at wire management, but our wire management, all it really does is we make sure that our wires can't ever get caught into something that's spinning or moving, because that would be awful. It would break the drivetrain, it would break that motor, it would destroy everything. We also want to make sure that no wires can get outside of the robot and be dragging all over the place. And additionally, that we know where all the wires are. So with this robot core, the three really important things: the structural stability, you have to use it to hold your robot together, which we do again with the quad block mounts and the U-channel. Getting your electronics in there, keeping them generally out of the way of most of the robot design, but still really accessible, as you'll need to reach them frequently throughout the season. And then keeping in mind wire management, keeping your wires together, out of the way, not super tangled, and never going to get caught in any other part of the robot. And so those are kind of what we think are the most important considerations when you're designing the core of your robot. Cool. The next part of our robot that we're going to talk about is our intake. Now, the intake is one of the super important subsystems of this specific robot and ultimate goal, but intakes are super important every year. And while the majority of what I'm going to be talking about is specific to the ultimate goal, I think a lot of the design elements that we use and principles are really applicable to the majority of seasons in FTC. So hopefully this will be helpful no matter what the game is, to kind of get a sense of how we built this intake and the reason we made the design choices we did. So for starters, just the basic overall design of the intake. So the rollers we have here are made out of go rail. We drilled holes through the go rail to slide in tubing. So it's one piece of tubing that goes through the go rail. And this is really important because it makes the tubing really easy to switch in and out if a piece breaks or if we wanted to change the length or the durometer of the tubing. So that was really important for the prototyping phase, because then we could test more or less stiff pieces of tubing, longer and shorter pieces of tubing with ease, because sliding them in and out of the part is not difficult at all. Also, because it's rigidly stuck like that, it means that the tubing itself can't start rotating around the axle. If we just had a normal Rex axle and we had a piece of tubing attached to it, which is a little bit hard to imagine, the tubing itself could start spinning around the axle instead of with the axle to push the rings in. So by sliding it through the center of the go rail, we get stability and easy access if we want to try to change different parts of the rollers. And so each of the rollers is supported on both sides, again for to keep the structural stability, to keep the intake structurally sound. And the power moves right here along with these pulleys, and it comes from two motors down here in the center of the robot. Both of these motors are 312 RPM motors from GoBuilda, and then out there's an external 1-to-2 gear ratio, which is really important because in this season we realized one of the kind of choke points that really slows down your scoring process is how fast you can intake the rings. And so by using two motors at a relatively high speed, we were able to keep the rings coming into the robot really quickly, but also because there's two motors, we weren't sacrificing the strength, which helps to prevent things like jams. If the tubing is strong enough to, say, if a ring's kind of stuck at a weird angle, to just push the ring through and get it to slide up the ramp. And also the opposite is true, is that if a ring is ever stuck somewhere, we are always able to either keep intaking it up the ramp or reverse it all the way back down out of the ramp, because it's always in contact with one of these 4 rollers. And so yeah, that's how we transfer the power. It's with the chain on the sprockets on the outside of the robot, bringing the 2 motors together, speeding them up, and then distributing it down across the 4 different rollers. One of the really cool things on our intake that we think is super innovative and helped a lot, if you can stop the op mode real quick, is this bottom roller here. And so, if you can see right here on the robot, we have what looks like another piece of long tubing, which it is. It's on top of small axle, and it's powered by this servo that is kind of just fit really snug into the bottom of the robot. And what this does is to counter rotating bottom roller. So it spins in the opposite direction of the tubing, but it lifts the rings up and off the mat super well. When they hit it, they get like the motion up from the roller on the bottom, and they're also getting pushed on top from the main rollers. And we found that this helped a lot with intaking speed and consistency. And it's really important for in-person tournaments when things like the material beneath the mats can change. And we practice on concrete, which is very firm material, but sometimes it'll be on top of carpet or something else, so it'll be squishier. So the distance between your robot and the actual mat will change, like how far your robot sinks into the mat. And so this helps prevent those sorts of variables at in-person play from affecting your intaking consistency and capabilities. Moving forwards, going to talk a little bit about our ramp system and our funnel system on the intake. So our ramp here is made entirely out of polycarb. It's a piece that we cut in our CNC machine, and then we bent up here to create a wall that funnels the robot from left to right into the top corner of the robot, where it falls into the magazine of the shooter. We really like this design for a couple reasons. One, we think it's the most simple design you could get for your intake. The actual motion of the rings to get to the shooter is almost entirely passive in terms of the direction that the rings go. They get pushed up by the tubing, but that just pushes them straight up. To get them into the actual right position, it's just a matter of sliding up the ramp and hitting the wall, which funnels them into the magazine of the shooter. To get this process to be super smooth and to reduce friction, we sanded down all the polycarb in the intake. So the ramp, the wall, and even the roof here and the transfer is all sanded down. And this is really important to getting the rings to be able to slide as quickly as possible without any friction. It reduces jams and it increases the speed of your intaking. So that's something really important to do if you're able to do it. And another thing that really set us apart last season and helped us a lot was our outer roller. So we have an adjustable outer roller on the front of our robot, which we can have in a couple different positions. We have it out front. Something that was really helpful was because during auto, you would have like a stack of 4 rings, and of course you can't intake 4 rings at a time. So we would be able to push down the rings with the front bumper and then intake them. And then in our highest scoring games of the season, something that we were able to do with our outer roller was put pleather on it and create sort of like a car wash mechanism. So the pleather spun, if you can imagine, here instead of the tubing. And what it was able to do is knock down rolling rings. Because an ultimate goal, if you want, you can go back and watch a video of the season and understand a little bit more about the game. When the rings come into the field, they're rolling at you, and you still want to be able to intake the rolling rings because that's the quickest way to be able to score. So with this adjustable outer roller, we had a middle position where you could put the roller up like that, and then you could intake a rolling ring, a vertical ring.
Works better when it's moving.
It definitely works better when the robot's moving towards it, and also with the pleather, but as you can see, it effectively knocks down the ring, which we realized was the most important part of getting the vertical rings to actually come into the robot, is not to be able to get something to ride up vertically, but to be able to knock them down to get into the normal intaking position. So 2 good methods for that. One is having something that rotates at kind of this middle height here. Sorry. And then also using material like pleather, which is really good at not moving the rings up the ramp, but knocking them down flat on the ground. And another little trick we figured out for this is right on the front. We have this kind of like corkscrew piece of tubing going around the rollers. It's kind of hard to demonstrate, but basically what it can do is it turns and it'll knock down a vertical ring as it comes into the robot, just like that. So we have a bunch of different ways on the front of our robot that we work to make sure that we can knock down those vertical rings and then intake them up into the shooter. And now something that's really important about in-person play in general with your robot is you're going to be interacting with a lot of unknown variables and other robots. Some people are really aggressive. Sometimes robots disconnect or are out of control. So what was really important to us was protecting our servos and this front mechanism on the robot. So what we did here is we actually suspended our outer roller of our robot. There's a rubber band here which is pulling the front roller back down to the ground, and the robot actually moves the roller using this servo, which is a servo on either side, and a zip tie. And what this allows is that if you put the roller into the middle position here, if another robot were to hit our robot, instead of moving the servo and forcing the servo to move, which would break it, what happens is that the zip tie itself, it shrinks because you can't really push on something like a zip tie or a string, which are both good materials to use here. But after the robot that hit it or the wall that we hit releases, the rubber bands pull it back down into place. So your servo doesn't lose position and you protect all of this and the servo from getting hurt. And this is kind of a really simple and elegant solution. I think it's not super complicated. You just need to find some way, two places to put a rubber band to grab the mechanism to keep it down and hold its position, and then use string to attach the servo in a sort of linkage, so that you still have control over the motion of the outer roller, but it's protected from contact that it will definitely experience in any sort of in-person play. And so, into sort of the prototyping of this robot, the two things we were really looking for in our intake were flexibility and efficiency and speed. So we really wanted our robot to be able to intake rings coming in at any angle, any position, if they were vertical, if they were flat, if they were stationary, if they were rolling, if they hit this side of the robot, that side of the robot. We didn't want it to matter. We wanted to make sure that the rings would come in quickly straight up into the shooter, because our game strategy was to be constantly shooting the rings. So we also need to be constantly intaking the rings. And so that came down to us testing a lot of different variables. We needed to get the right amount of rollers in here so that rings were constantly, being pushed up the ramp without like cramming too many things into the middle of the robot. Something that turns out is really important is your surgical tubing choice. And so a lot of teams use different methods for how they actually move the game elements. For instance, again, with Ultimate Goal, it was rings in their intake. A lot of teams will use an Omni wheel or some sort of smaller wheel, a Gecko wheel, to move elements into the robot. For certain games, that's super effective, and for other games, it's not as effective. We personally think tubing is like the perfect, it just works for everything. It doesn't matter what the shape or size of the object is. It's super flexible, it can move in all directions, but it still has enough rigidity to move the elements up through your intake system. So we think tubing's a great material to start off with when you're prototyping and you're testing different elements. Or different materials to move the game elements through your robot. Things like wheels are also good things to test. So if you're looking to test out an intake, I think a lot of the principles we talked about here, again, are applicable to different seasons. So if you can get your hands onto any sort of game elements, whether it's rings, whether it's the blocks and balls from any of the previous seasons, just practicing building different sorts of intake and remembering the key things of different materials used, and if it's tubing, it has to be stationary, it has to be supporting the rollers on both sides, again, and just, working through it, trying different speeds and strengths in the motors until you see what moves the objects most efficiently and most consistently through your robot. And so, again, intaking may seem like something that's sort of trivial, and as soon as you can get something into your robot, it's done, it works. But in our experience with this season and with other seasons is that the speed of your intaking can often determine just how good your robot can be. And so for us, the last sort of piece that took our robot from being very good to being one of the very best in the world in the Ultimate Goal season was that we were finally able to get our intake by way of the two motors and all the different things we tested within the intake to be one of the fastest in the world, and that really took our robot up into the upper echelon. And yeah.
Talk about after talking about the intake is how you transfer the game elements from your intake into the rest of your robot. So this was a very, very challenging task for us this year. As you can see, these are 4 of our 18 different iterations that we tried for just this one piece on our transfer, because essentially it's so important that you get the rings, or in this case the rings, but just in general game elements from random all over the field, sort of random bouncing around the inside of your intake, to be exactly where you want them to be in your scoring mechanism. For example, in Ultimate Goal, we wanted the rings to stack 3 high right here. And if they were if they can't be sticking out the side here or anything like that. So this transfer has to be able to get rings that are bouncing all around on the inside of the intake. Not perfect orientation, sometimes slightly on top of each other if they're coming in 2 at a time, into very perfectly just 3 on top of each other. So to do this task, we did a lot of slow motion, just sort of sitting here, feeding rings into it over and over again, trying to create jams and trying to figure out where jams are coming from. And this was the iteration that we settled on, mostly because it did not reduce all jams. There were still a lot of jams with this, but all of the jams that occurred with this design were fixable during a match. They weren't match ending. It's not like our intake was permanently jammed, whereas some of these earlier iterations, you imagine this right here, it's so tall that if something gets jammed way up here, there's no way that this tubing is gonna be able to touch it. And an important thing to talk about, also just an important technique that we use for this, is bending polycarb. So you can see all of these were originally cut out on our CNC as just a flat sheet of polycarb. And then we used a heat gun, which I will show you in a second, to bend them to be exactly the right shape. So if you come over here, this is just a demo that I have set up. So this is just a random piece of polycarb that we have lying around right now. And essentially we have one part of it stuck rigidly to the table with these 2 clamps, and then this part, which is free to bend. And then what we would do is take a heat gun and heat up this part of the polycarb really, really hot. We have this special thing on our heat gun that helps it go directly into the gap in the wood. Heat it up until it starts to melt just a little bit, but it's not liquid yet. It's just very, very flexible. And then pull it down until it's at the right angle, and then just hold it there as it cools. So that is how we got bends like this, just very, very, this is actually a very bad example. This is a better example. Very, very accurate in angle. Sometimes we would even cut in polycarb, basically a protractor, to see exactly what angle we want it to go to. And another technique that we used for this later this year, not for this robot, was cutting in a little groove into the polycarb before we bent it. So you can kind of see there's a little groove right here. Maybe if you do a side view, that'll work better. And that just helps the cut be, the bend be in exactly the right space. The next mechanism we're going to talk about is our shooter. So our shooter works with these 2 motors right here from GoBuilda. They are the gearbox-less motors, or just direct 1-to-1 ratio. And then in here you can see that we have a gearbox. These 3 gears are steel gears, also from GoBuilda. And essentially the idea is just to get power in as frictionless a way as possible and as direct a way as possible to just get rid of any sort of failure points, because this is spinning at very, very high speeds, and just transfer it directly to the wheel. So another important thing to note is that this wheel axle right here, you can see the very top of it coming out of the gear right there. So you can see there's actually a bearing hole right above it, cut into the plate, because we originally had a bearing there, a bearing on this top plate right here, this big black one right here, and then also on the bottom plate, which you can't really see. What we found though was that that caused a lot of friction in the axle, because essentially we were over constraining it by mounting it with 3 bearings in 3 different places. And theoretically that should work fine, but if there's any sort of misalignment between any of the plates, then the axle will have a lot of trouble trying to spin, especially at 4,000 to 5,000 RPM, which was what our shooter was spinning at. So that was a problem that we encountered a lot during the season, just reducing friction in the system since it's such a high speed and just really crucial. Let's see. Another important thing, so I've taken our transfer plate off here, which is why you can see right into it, is controlling the rings once they've actually landed in the shooter. So you can see that we have 2 servos in here. So this one with the big scythe on it will push the rings into the flywheel right through there. And then this one with the much shorter arm prevents the rings from drifting into the flywheel before we push them in. So I can demo that for you right now. So you can see that this arm right here will prevent the rings from being pushed in the shooter by accident. So say if you're driving along, you get hit really hard from the side, there's no way that the ring could accidentally just end up over there. Like if you push it really hard, I guess it would, but that's never gonna happen. So it's just there to help control the rings. And this is obviously very game specific to Ultimate Goal, but just in general, that's something that you really wanna think about, is just really controlling your game elements once they've entered your robot so they don't accidentally score early if that's something that would be able to happen, or just fall out or anything like that. You want to keep very good control of them. And now onto our flywheel. Yeah, I got it. So our flywheel in here, similar to the intake tubes, this was something that we just did a lot of prototyping on. So what we ended up choosing was a green Andy Mark Stealth wheel, but we tested all different durometers of Andy Mark Stealth wheels, or also compliant wheels we tested early on in the season. And that testing was just so important, because otherwise we would have ended up with a wheel that just was not the best at shooting the rings out. And designing something as crucial as a shooter, if you're starting from like the not as good starting point of not having the most optimal wheel, then you're just gonna have a more difficult time designing, and it's not gonna work as well throughout the season. And just also, if you do another close-up of this, you can see that the wheel is very worn down. There's all this flakes coming off, and you can see the part that actually contacts the rings in the lower half is actually a little bit thinner, or a little bit dented in compared to the top half, which never contacts the rings. So this was actually a problem that we encountered at our state tournament, where it was an online tournament. So we were practicing throughout the week and it was all going good. And then the night where we started recording our first matches, rings started missing over and over again. We couldn't figure out why. And it was actually because this wheel had worn down to the point where it was not effectively shooting the rings out, and they were just sort of flopping out in front. It's a bit of an exaggeration, but they were just missing. We could not figure out why. So that was a really big lesson for us. Identify any parts of our robot that are gonna be breaking over time. In this robot, it was very much this flywheel. In other robots, it could be a very crucial belt that's being pulled in weird ways. We had that issue this year. Or any sort of compliant wheel is gonna give you that issue if used a lot. This rubber is a big issue. Any sort of springs or rubber bands. If we had these rubber bands on for a long part of the season, then we would have had to replace them over and over again, because they're obviously going to be under a lot of stress. Yeah, that's just very important to think about. Another part of our flywheel that's really important is that we actually have 2 big circular aluminum plates on the inside of it. So I'm not sure there's really any way that we're gonna be able to, you might be able to catch a glimpse of it right through there. Just that little shiny bit. They're fully inside of the wheel. And we did this because it increased the moment of inertia of the flywheel, which we found through testing helped make the ring shoot out much more consistently than if it was just being powered by the motor and that was the only force that was being transmitted to the ring. If the wheel's super heavy like this, it allows it to spin up to a really high speed and then it's very resistant to being slowed down, which also makes it more resistant to any sort of friction or anything like that. And let's see. Oh, the last part of our shooter, and probably the most innovative, is this turret design. If we aren't fully facing the goal, say like goal's over there, we turn like this. This shooter, or this turret, or partial turret I guess, is able to turn just that extra few degrees. It only has about 60 degrees of freedom, 30 in each direction. So it's not a huge tool that we can use to shoot from like anywhere in the field at any orientation, but it allows us to correct for any sort of minor inaccuracies in the angle of the drivetrain, or if we're moving also. This turret is able to adjust for that movement and shoot out and basically counteract the robot's movement as the rings come out. And just to see mechanically how this works, this servo right here has a gear right under it, which again, you're probably just gonna be able to catch a glimpse of. It's brass, and it's connected to this gear, which you can't really see, but it's connected to this. So this was just a really clean way of integrating this into a robot without having a whole huge complicated turret setup. And I think this is an important lesson in strategy also, because in Ultimate Goal, a bunch of teams did turrets and a lot of them worked really well, but also if you don't have all the time or resources to dedicate into something like that, or for example, we were a rookie team last year, so we weren't confident that we would be able to actually make a turret that would work well. If you try to build that sort of super complicated design, it's either going to work for you or it's really not going to work for you. This we thought was just a nice sort of middle ground between those two things, of an easier design that we could integrate into our pre-existing shooter design, while also still having a lot of the functionality that we wanted from the turret. And yeah, so also, same as the intake, all the polycarb on the inside of the shooter is very sanded down. It's extremely smooth, which just allows the rings to sort of glide all the way over it. And another example of bended polycarb, these walls right here, this entire curved wall on the turret hood, as well as the normal wall of the shooter, are all bent polycarb, which allowed us to get like a very smooth, perfect curve more than any sort of rigid aluminum part or rigid 3D printed part would. Yeah, I think that's all I have to say about the shooter.
Higher scores. Wolfpack going and grabbing their wobble goal. Same thing with their teammates, throwing them both over on the other side. Black Forest Robotics.
All right, so the last sort of subsystem on our robot that we're going to talk about is the claw mechanism on the back of our robot, which is our Wobble Gripper from this season. And I'm going to walk through a couple of the design considerations that were really important to making our Wobble Gripper. So one of the first things that we were thinking about in our Wobble Gripper is that the goal for this part of the game was that you needed to pick up the wobble goal and then drop it over a wall that was just about a foot tall, I believe. And so that means that you need to have a pretty wide range of motion to be able to grab the wobble goal from down here and then get it up to a height like this where it could be dropped over a wall. But the problem is that the wobble goal itself is relatively heavy. While on its own, that's not a huge problem. With our arm needing to reach out so far to be able to grab the wobble goal so that's not actually making contact with the robot, it adds a lot of leverage out onto the end of the arm, which meant that the servo and the mechanism moving the arm needed to be really strong. And so we have a torque servo here that we geared for extra strength by going from a smaller gear to a larger gear. It means that we get less rotations out here for each rotation that the servo takes, but it also means that the mechanism itself is much stronger. But a really important thing to note about servos is that they have a limited range of motion. Servos come with only 300 degrees of motion when they're in servo mode and not continuous rotation mode. And so, like I said before, we're dealing with two things here. We're dealing with the weight and the leverage that's put onto the system by actually moving the wobble goal, but then also making sure we have a wide enough range of motion to get the wobble goal out of the field. And so something we had to test out here was the balance between changing the gear ratio to get more strength, but also making sure that we maintain a wide enough range of motion. So when you're working with servos, you need to take into account both of those things. You don't want to put too much stress onto the servo, and you want to make sure that you get the full range of motion that you needed. Nowadays, there are 5-turn servos, which give you all the like degrees and range of motion that you would ever need. But if you're working with just torque or a speed servo, those are things you need to be aware of. I think also that our claw separately, just as a side point, is a really good example of integration, because we're trying to get everything to fit together onto the robot, and it fits really nicely onto the roof of the shooter. We maintain the strength and stability. We don't sacrifice anything in terms of strength or stability. And we also found a position where we get the Wobble Gripper to be like, it's really easy to get to the wobble goals and things. So like placement on the robot is also really important in terms of where you didn't put different things. So we'll get into the strategy of that a little bit more later. And the last thing that I want to talk about with the Wobble Gripper is how we actually grab and how we just came up with this strategy for the 2 interlocking claws for grabbing the wobble goal. So if you can see here, we have 2 servos that we use counter-rotating, so the claws spin in opposite directions, and they interlock here. If you can see, one claw fits inside of the other 2 claws. And just a little bit side note here on servo protection, by using having this gear train so that this is the actual thing moving, it takes a little bit of the stress off the servo, and you want to, as much as you can, make sure that when you're powering something with the servo, it's not directly powered just off of the servo itself, but something that the servo is powering. So on the front we have the linkages, here we have this gear train. Now the shape of the claws here and the way that it moves allows for 2 really important things. One is that when we have the Wobble Gripper into its ideal position, it actually has 5 points of contact with the gripper, which means it is held really securely into place. It's not going to shake around. It's not going to fall out of the robot when it's being lifted up. So that adds to the consistency. And then the last really important thing is that because of the wide range of motion of the claws and the shape of them, we can grab the wobble from various different locations, and it'll fall back into the ideal gripping location. We don't need it to start here. It could start out here somewhere, and the claws will pull it right back into the position that we need it to be to actually move the wobble goal. So grippers are something, or claws aren't something that are always used in games, but they are used, occasionally in different seasons. Sometimes they're used as intaking mechanisms or scoring mechanisms, and so those are the main ideas behind our Wobble Gripper.
Lions is trying to go ahead and do the same. All the power shots down for red, trying to get up to 400 points here. Looks like they're going to get pretty close with that wobble goal delivery. That might have just secured it.
We just went over all of our different subsystems that we had on our Ultimate Goal robot. That might have been a little bit intimidating if you're just starting your new season right now and you're trying to figure out the best way to attack the game from the start. I just want to say, this is not at all how we started our robot. For example, our intake at the start of the Ultimate Goal season was just a piece of polycarb with a roller on top of it, and then we would swap in different wheels or different pieces of tubing onto that roller, and it just allowed us to test out tons of different things. And we didn't need barely any custom parts. We had a big polycarb panel that we used, but we could have just as easily used a piece of wood or anything like that. But it was just such a crucial step, because otherwise we would have had absolutely no idea, no base to go from for the length of the tubing, how far apart the rollers should be, what material the rollers should be, really anything about our intake we really could not have known without going through that prototyping process. Another example for our shooter. This is a very, very sort of well integrated into the robot design. Our first design was just a piece of MDF with thin MDF walls and a wheel that was directly attached to one motor. And we just swapped in different wheels into that motor, different motors to test different gear ratios. We would have never known that we needed 2 motors for our shooter. We would have had absolutely no idea what sort of gear ratio we would want. And the only way that we could have found that out is by testing those original sort of more free-built, simpler designs, and also just not at all worrying about the integration. So all of these designs were just way too huge to fit onto a robot, way too bulky. They were not at all intended to fit onto a robot. And just having that design freedom, knowing that that the design that you're making, well, you don't have to worry about integrating it to anything else at all, really allows you to just focus on what you need to test for an intake, if that's tubing, for a shooter, if that's what type of wheel to use, what type of gear ratio to use, for a drivetrain, if that's what type of gear ratio to use, what type of wheels, really for everything. just such a crucial step to go through that prototyping process.
Well, we hope you found this video helpful. We were trying to think through a lot of the different design considerations and parts of making a robot that would have been super helpful to us when we were first starting out. And so if there's just kind of big takeaways that we want you to be thinking about when you come from this, that there's a lot of things to think about when you're going into a season. You don't have anything to start off with, and you have a bunch of challenges to tackle. And you can see just how long this video ended up being in our explanation of our robot. So yes, it's super complicated and there's a lot of moving parts, but the way that you can really get to the top level or just to a competitive level where you're making subsystems and parts of your robot that are effective at completing the challenges of the game is just working through it and trusting the process. Isolating something, like we said, like just the intake and testing out different ideas, testing out different tubings, that sort of thing, until you get to a final design. And that doesn't need to immediately go on the robot. That can be completely separate. Same with the shooter and same with everything, is that as long as you have fundamentally sound design principles, that you're considering different things like the durometer of the tubing, the materials you're using, the relative strength of the materials, the shape of the game objects, and the goal of the game. That if you really take into consideration a bunch of the different things that we talked about during this video, as you work through your different parts of your robot and subsystems, that you can create something competitive and you can create something high level. And it doesn't rely on these custom parts. So many teams from all over the world who are really top teams are able to make their robot with almost no custom parts all over it. And so just trust the process. At the start of the season, just get right on it. Start trying every idea you have, seeing which ones work, and just running away with that. And then, as you go along, there's more complicated things that you run into. You need to worry about the stability. You need to worry about integration, fitting everything together, which is something that can be a little complicated, but hopefully you can learn a little bit about design and a little bit about how to attack a game and how to make a fundamentally sound robot that is also super competitive from this video. So thank you.